All right, so what we're going to do is I want to kind of walk you through some of the assignments from DeltaMath that go along with your practice problem sets. So what you're going to see is sort of 5 different types of problems that you're asked to work on, focused on key features of polynomials. The first type of problem is just on having you identify y-intercepts of polynomials. Obviously, you could work these problems out using Desmos, right? Just verify that you're typing in the exact equation like we see here. F of x equals 2 times 4x plus 3 times x minus 4. The other way you can calculate the y-coordinate for your y-intercept is to plug in 0 for x and simplify. So for example, if I plug in 0 here, then this becomes 4 times 0, which is just 0, plus 3. That makes this parentheses a 3. So now I have 2 times 3. And then over here, if I plug in another 0 for this x, 0 take away 4 is negative 4. So then this simplifies to 2 times 3 times negative 4. And if we multiply these out, 2 times 3 is 6. 6 times negative 4 is negative 24. Now I did that just kind of talking through it, but obviously I would expect you to go through and to just take a piece of paper, work it out by hand, and show that you know how to find the y-intercept with Desmos, but also without Desmos by plugging in 0 for x. Okay, we submit that. There we go. Let's do one more of these. Once again, if I plug in 0 for x, that's going to help me find the y-intercept. So if I plug in 0 here, this is 2 times 0, or 0, times this parentheses and this parentheses, right? Plugging in 0 here would make a 3. Plugging in 0 here would make a 0 plus 6, or just 6. So we end up with 2 times 0, 0, times 3, times 6. But if you think about it for just a moment, 0 times anything is 0, and then that times anything is still 0. We're going to end up with a y-intercept of 0 for this one. Okay, and we see that happening. Now I'm going to do a couple more, but this time with Desmos. So obviously, if you go to Desmos, and just to be in a good habit, let's do NC Math Desmos. Use the testing version. That way we know exactly what features we can and can't use. So if I type in this equation, f of x equals negative parentheses x squared plus 3 to the third power. Then I want to zoom out until I see this graph. Okay. Looks like the y-intercept is down here. There we go. When x is 0, y is negative 27. Perfect. So that's how we go about finding the y-intercept, both by hand, plugging in 0 for x, or plugging in the equation and then looking at Desmos and identifying where that y-intercept would be, where it crosses the y-axis. So that's your first type of problems. Your second problem set deals with determining features of polynomial graphs. So in this example here, the polynomial function f of x is graphed below. It's asking you to fill in the form below regarding the features of this graph. So the first thing it asks is about the degree. Remember that the degree of the polynomial can be identified by the number of sections where we're changing directions, right? So increase, decrease, increase, decrease, increase, decrease. Just going back and forth. So I'm going to go back and count those. 1, 2, 3, 4, 5, 6. That's an even number of pieces. That would be an even degree. The other way I know that it is even is notice that both of the arms end up pointing in the same direction. In this case, they're both pointing down. Okay. If they're ever pointed in opposite directions, one arm up, one arm down, then you know it is an odd function. But because both arms extend to the same direction, it's even. Now the leading coefficient, if we look at where it ends up, if it ends up pointing downward, then you have a negative leading coefficient. If it ever ends up pointing upward, then you have a positive leading coefficient. Whether it's an even degree or odd degree doesn't impact this. You always look at where you end up, and that helps you to identify positive or negative leading coefficients. Now, next part, there are how many distinct real zeros? Let's go count the zeros. 1, 2, 3, 4, 5, 6. We see 6 real zeros. And how many relative extremes? Now, what does this phrase mean? Relative extremes is talking about maximums and minimums. And again, it doesn't have to be the maximum for the whole graph or the minimum for the whole graph, just for sort of the neighborhood. If you were to imagine zooming in on this little part right here, that's clearly the maximum for this section. And then we have a minimum down here, then another maximum, then another minimum, then another maximum. So we end up with 3 relative maximums. These are the top points of each little hill. And then we have 2 relative minimums. That's a total of 5 relative extremes. Okay. Notice they've got them highlighted there. I'm going to do this again. Another example. Here we have another polynomial function graphed. Our job is to fill in the form once again regarding the features of this graph. What's going to be the degree of this one? Well, notice how both the arms are pointed up. That's the same direction. That always happens with even degrees. But let's count them just to check. So if we come down 1, then up 2, down again 3, up again 4, down again 5, up again 6. And that is an even number. So it does match what we saw based off of the arms. Because the right arm ends pointing upwards, we know our leading coefficient is positive for this polynomial. How many distinct real zeros are there? 1, 2, 3, 4, 5. Now, why would we only have 5 real zeros if on the last one we had 6 and we thought this also had a degree of 6? Notice this one right here. The graph bounces off. Remember, that means that there's a multiplicity of 2 there. That particular 0 would actually count as 2 of the solutions or 2 of the zeros. So technically there are still 6 values, but only 5 of them are distinct, are unique from each other. Okay? If one of them counts more than once, it is only counted once in the terms of distinct zeros. Okay? 1, 2, 3, 4, 5. And then finally, how many relative minimum points do we have? Well, right here where we changed from decreasing to increase, there's 1 minimum. Here's another minimum, 2, and another minimum, 3. So we'll submit that. And we got that one right. Let's do one more of these. Here we have another polynomial. Once again, filling it in. What is the degree going to be? Notice that the arms are in opposite directions here. Remember, equal directions means even if they're both pointed in the same direction, but if they point in opposite directions, one down, one up, that is odd. Opposite is odd. Let's also count the sections and see if it gives us an odd degree. 1, up, down again, or down is 2, up again 3, down again 4, up again 5, down again 6, up again 7. That would be an odd degree. Where do we end up? We end up pointing up, so this is a positive leading coefficient. There are how many distinct real zeros? 1, 2, 3, 4, 5, 6, 7. 7 distinct zeros here. And how many relative extremes? Remember that extremes means maximums and minimums. So we have 1, 2, 3 maximums and 1, 2, 3 minimums. 3 top points and 3 bottom points. So that's a total of 6 relative extremes. We're going to submit this, and we see we got it correct. So you're going to be asked to answer several of these in your practice. Try to see how many of these you can get correct. Next up, increasing versus positive graphically. So this function is graphed below. What's true about the graph on the interval from point C to point D? So from right here to right here, what's going on? First off, is it positive or negative? Well, from C to D, C is starting at 0, but then it immediately goes up into the positive y values, right? This is one of the positive sections of the graph from C to E. So it's not going to be negative. Now we just need to know, is it increasing or decreasing? Well, from C to D, we're going up and to the right. That is increasing. So we're going to select positive and increasing. Wonderful. Let's take a look at another one. What is true about this graph on the interval from C to infinity? And that's a positive infinity. So that means start at C and go to the right to positive infinity. What's happening over here? Well, I can tell that the graph is going to be negative because it's below the x-axis, but it's also going downwards, so that's decreasing. So we have a negative and decreasing section. I'm going to submit that. Let's do one more. What is true about the graph on the interval from negative infinity to a? That's going to be this little piece over here. It's where it starts on the left, going towards negative infinity, going as far as we can left, but then going right up to this point A. Well, right here, it is above the x-axis, so it is positive. But from left to right, this line, this part of the curve is decreasing. It's going downwards. So we're looking for positive and decreasing on this one. All right. So that's what you're going to be doing on the third section. Let's go to section 4. Increasing versus decreasing and positive versus negative. We're going to call this level 2. Now what we have to do here is look at what they're asking us to give intervals for. In this case, it says in which f of x, that's like the outputs or y values, are greater than or equal to 0. So when are the y values positive, because it said greater than 0, or equal to 0? So we were practicing writing our positive intervals where we would use a parentheses and we would say, okay, we need to look from this starting number to this ending number. But there is a different way we can write intervals. We can use just standard standard comparison notation where we're using less than signs and greater than signs, things like that. So when does this graph first become positive? Well, it's switching from negative at the beginning to positive at the number -7. And because it said we can also focus on the ones that equal 0 as well, so positive or equal to 0, I want to say that when -7 is less than or equal, you can either click the button or type less than and then an equal sign, less than or equal to x, and then it stays positive and it stays positive, it stays positive all the way till I get over here, and then at 4 it's going to switch. Right at 4 it's still 0, so we're going to say less than or equal to 4. So that's the first piece where it's positive. And then it goes negative for a while, from 4 all the way over to 8. And then it becomes positive again. So then I'm going to say there's a second piece. So I'm going to use this little OR button. So it means we can pick any x in here between -7 and 4, or any x that is greater than or equal to 8. Okay, pick any x bigger than 8 or equal to 8, and it's going to give you an output or a y value that's 0 or positive. I'll submit that answer. We got that one right. Let's do one more of these. Determine all intervals on which the outputs are less than or equal to 0. Well, I can see right away this graph has negative values at the beginning, and that's what I'm looking for. When are my y values or my outputs, f of x, less than or equal to 0? So at the very beginning, if I can pick any x to the left or less than -8, but not just less than, I also want to include the equals because this particular expression says that it's okay to equal 0. So it's negative there, or it goes positive for a little while, and then it's back to negative at -5. If I pick any x greater than or equal to -5, and then it at 5, it gets back to 0, but then it goes right back to being negative. So it never actually switches back to positive. So at this point, I'm basically saying, okay, pick any x bigger than -5 or equal to -5, and you're always going to get a value that's either negative, or in the case of 5, 0. So I don't actually have to put an upper bound. I don't have to tell it that my x's can't get any bigger than some value here. We're going to submit this, and we got that one correct as well. All right, coming back, let's look at the final section. Determining the domain on which the following function is increasing. In this problem, you're just telling me when is the graph increasing or when is it decreasing, and you're giving it to me as a domain. So increasing, that's going to be this left side of the parabola. That's going to start at x equals 0, and then it's going to keep increasing until I get up to the very top at 5. And when we're describing increasing or decreasing, if there's any starting points or any points where it switches from increasing to decreasing, we actually don't use equal signs on those. So I'm going to say when 0 is less than x and less than 5, x is less than 5, so just this little piece right here, from 0 to 5, that gives me the window of the graph. Notice how they color it in from your answer choice. That gives me the window of the graph where it is increasing. We do a couple more of these. Determine the domain on which this function is increasing. Well, it's decreasing on the left side, but then it reaches the bottom and it starts to increase again. Remember, we don't focus on the y value, we focus on the x. When did it switch at the bottom? It switched at x equals 2, and any x's to the right of 2, anything bigger than 2 for x, is going to give me an increasing graph. So x is greater than 2. Notice how this graph goes on forever. It doesn't just end at a point. Makes it a little bit different than the last one. There we see increasing over here. It would have been decreasing for all values less than 2. One more. Determine the domain on which this function is increasing. Notice this one doesn't have the arms extending forever with arrows on the ends. So we start at x equals 0, and we're looking for increasing, and it is increasing. For x is bigger than 0, but less than, once we get to the top, it's going to switch, but to decreasing. So where is that switch happening? Looks like it's happening at x equals 7. So pick any number between 0 and 7, and it's increasing. And once again, we see that on the graph. Okay. Now, I think all my questions were typically increasing, but you should see a mix of increasing and decreasing. So take your time on these. Again, if you've watched through the whole video all at once, remember you can go back and kind of pause the video and skip around to find the exact types of problems you're currently working on DeltaMath. But try to get through all of those sets, answering as many questions as possible. All this practice is really just going to help you really make sense of how to answer these types of questions on polynomial key features. So good luck. And then on Wednesday, when I'm back in the classroom, I'm happy to give you any extra assistance if you need it still. So good luck.